All right, let's get right into it. You've probably seen this happen, right? You ask an AI the same exact question, and you get two totally different answers. It feels random, kind of like there's a ghost in the machine. Well, today we're going to pull back the curtain on this whole technical mystery. We're going to figure out why these large language models can be so darn unpredictable. And we're basing this all on some really fantastic research from the folks at the Thinking Machines Lab.
I mean, it's a question pretty much anyone who's used an LLM has asked themselves. You spend all this time crafting the perfect prompt, you get an amazing response, and then you try to do it again, and you get something completely different. It's not just frustrating, it kind of breaks our whole idea of how computers are supposed to work.
And this is where things get really strange. Now, you might just chalk this up to the AI's creativity doing its thing, but this happens even when you crank that creativity setting, the temperature, all the way down to 0. That's a setting that, in theory, should make the model totally deterministic. It should always pick the most likely next word. So, what on earth is going on?
To get to the bottom of this, let's start with the usual suspect. This is the explanation you'll hear most often, the one that's all over the internet. We'll call it the concurrency plus floating point hypothesis. It sounds a little technical, but the core idea is actually pretty simple.
So the first piece of this puzzle has a fancy name, floating point non-associativity. All it really means is that in computer math, the order you do things in seriously matters. It's not like the math you learned in school. Because of how computers have to store numbers, adding A and B first and then C can give you a slightly different result than adding B and C first and then A.
And here's a killer example of how this plays out. Let's say you add a tiny number to a gigantic one. The computer's precision just can't handle it, so that tiny number basically gets erased, rounded away into nothing. But if you handle the two huge numbers first, they cancel each other out and that tiny number survives. You've got the same numbers, just a different order, and you get a completely different answer.
Okay, so here's the theory everyone lands on. Step 1. GPUs are these parallel powerhouses, just crunching thousands of numbers all at the same time. Step 2. We know that floating point math cares about the order you do things in. So you put those two together and the conclusion seems obvious. All that parallel processing plus the quirky math, well, that equals unpredictability. It all makes sense. Case closed, right? Well, not so fast. Because when researchers really started digging into this, they found a huge flaw in that theory. A crack in the case, a piece of evidence that just didn't add up. And this brings us right to the heart of the mystery. If the combination of parallel computing and floating point math is the real bad guy here, then why are some operations on a GPU perfectly, 100% predictable?
The researchers ran a really simple but super revealing experiment. They took a basic matrix multiplication, which is like a fundamental building block of any LLM, and they ran it 1,000 times on a GPU. And the result? It was bit for bit identical. Every single time. The usual suspect theory just completely falls apart right here.
So now we're staring at this massive contradiction. The individual math operations, the kernels, they're deterministic. The entire server is deterministic if you feed it the exact same batch of requests. But for you, the single user asking a single question, the output is still all over the place. The mystery just got a whole lot deeper.
So it's time to unmask the real culprit. And it turns out the problem isn't about the order that parallel calculations finish. The problem is about how many calculations are being done all at once.
This leads us to a really key idea, batch invariance. In a perfect world, the math for your one request shouldn't change at all based on how many other people are using the AI at the same time. Your result should be invariant to the batch size. But in the real world, it's not.
And here's the chain reaction. The number of people hitting the AI server is constantly changing. It's totally unpredictable. Sometimes your request gets bundled in a small batch, sometimes it's in a massive one. And that changing batch size actually forces the GPU to use slightly different math strategies. And because of all that floating point weirdness, the final numbers for your specific request get changed along the way.
This comparison just lays the problem out perfectly. So on one hand, you process your single request all by itself. You get an answer. On the other hand, you process a huge batch of requests from tons of users, and then you just pull out the answer that belongs to you. Logically, your answer should be exactly the same in both cases, right?
But they're not. They're not even close. The difference between those two results is a whopping 1,669. And let's be clear, this isn't some tiny little rounding error way out in the 7 decimal place. No, this is a huge deviation. And it's caused by one thing and one thing only, changing the batch size. This right here is our smoking gun.
Okay, so we've found the real culprit. Now what? How do we actually fix this?
Well, the answer is to go back and re-engineer those core math operations to make them batch invariant, to make sure they give you the same answer no matter what the batch size is.
The engineers tracked the problem down to 3 main operations. For every single one, the problem was basically the same. To be as fast as possible, the GPU was changing how it did the math depending on the batch size. So the solution, in principle, was simple. Force the GPU to use one single consistent method for the math every single time. You might lose a tiny bit of speed, but you gain perfect predictability. The fix for the attention mechanism is a perfect way to understand this. So think of the AI processing a sentence. The old, unpredictable way would split that sentence into, say, 4 equal chunks. But if you give it a longer sentence, the size of those chunks changes, and so does the math. The new, deterministic way splits the work into chunks of a fixed size, always. This makes sure the math for each piece stays the same, and that brings back the consistency we need.
So after all that complicated engineering, did it actually work? Let's take a look at the payoff, because the results are honestly pretty amazing.
You know, a picture is worth 1,000 words. The researchers asked a standard LLM the same question 1,000 times, and they got over 80 different answers. But then, after they put in their fixes, they ran the test again. The result? 1,000 runs, one single identical answer. That's perfect reproducibility.
And these differences really matter. The standard model was actually consistent for over 100 words, but then it started to drift. Some answers said Richard Feynman was born in Queens, New York. Others said New York City. These tiny numerical errors can actually bubble up and change the meaning of the text.
So why should you care about all this? Well, getting true determinism is a massive game changer. It means we can do reliable scientific experiments on these models. It makes debugging them way, way easier. And it unlocks some really advanced AI techniques that were basically impossible before because of these tiny numerical shifts.
I really think this quote from the researchers just nails it. It's so easy to just throw our hands up and say, these systems are too complex, that these are just quirks we have to live with. But what they showed is that if you're willing to dig in and really understand the root cause, you can actually engineer a solution.
And that kind of leaves us with a final thought, doesn't it? This whole problem, which seemed like some fundamental, unavoidable property of AI, really just turned out to be a solvable engineering puzzle. And it really makes you wonder, what other unsolvable problems in AI are just sitting there, waiting for someone to find the right diagnosis?